It is with great pleasure that I'm able to introduce our speaker tonight, Dean of the College of Sciences, Paul Goldbart. Dean Goldbart, sure, why not? Applause. Dean Goldbart earned his first physics degree from Gonville and Keith College at the University of Cambridge in England. And I was surprised to learn today that Keith College has graduated 14 Nobel Prize alum, which includes this year's 2016 Nobel Prize in Physics, Professor Kosterlitz, currently at Brown University. Shortly after leaving Keith College, Dean Goldbart earned his PhD in physics from Imperial College with a thesis in theoretical condensed matter. In 2011, Georgia Tech was very lucky, and we were able to lure Dean Goldbart to chair the School of Physics here at Georgia Tech. And I might say, when he came, one of the first things he did was strongly encourage more public outreach and lectures just like these. His research areas are truly varied and include fields such as soft matter physics, disordered systems, superconductivity and superfluidity, ultra-cold gases, quantum information, and plain good old-fashioned theoretical physics. Dean Goldbart is currently a fellow of the American Physical Society and the Institute of Physics. More recently, Dean Goldbart was named the Betsy Middleton and John Clark Sutherland Chair of the College of Science. To many graduate students, however, he's probably best known for his seminal textbook on mathematical physics and graduate study. Show of hands, anyone in the audience used that book? A few, yeah? Tonight, I am very thankful that Dean Goldbart has graciously agreed to explain this year's Nobel Prize in Physics because it confused me, and I really wanted to understand it. Please join me once again in welcoming Dean Paul Goldbart.
Well, thank you very much indeed, Ed, for your kind introduction and for everything you do for outreach lectures here at Georgia Tech. Thank you very much indeed. And thank you to all of you for coming out tonight. I'm really thrilled to see you here. We'll spend 55 minutes, something like that, together at the intersection of beauty and impact, and together we'll spend some time following the dreams that have been had by some truly wonderful, thoughtful, imaginative people, and as we explore the physics that goes into this year's Nobel Prize, which I have to say I think was a truly marvelous one. Maybe we can have the slides up on the screen. So my subject tonight is strange and subtle states of matter, the topological ideas behind the 2016 Nobel Prize in Physics. And here are the three folks who were rewarded appropriately for their beautiful work. We have David Thouless on the left here, Duncan Haldane in the middle, and Mike Kosterlitz on the right. And I'm fortunate to know all three of them, not all of them very well, but I know all three of them, and all three have served as a great inspiration to me during my career, but also to many, many other people. We'll see later on during this talk that this is a much better representation. So these are sketches, we might call them coarse-grained representations where the details don't matter too much, and I hope to convey later on the idea that one of the beautiful things about theoretical physics is there is a concept of what's called a minimal model, and that minimal model really captures reality in some ways better than the fine-grained detail that we think of when we first look in the box and ask what is there in our experimental equipment. I also want to just spend a minute saying a word about Vadim Berezinski, who was a brilliant physicist in the Soviet Union, many of whose ideas were at least early, and in fact more than just early, precursors to this year's Nobel Prize, and he unfortunately died at a very young age. There is a beautiful obituary of his work that you can find in this reference here, and I think I'll find another laser pointer, because that one seems to have died. This one is just great. Now, a lot of what I'm going to talk about tonight is captured in this lovely book. It really is gorgeous, and if you're going to buy one book in this subject, I would recommend this one. This is a picture of a relatively young David Thouless when he was a student at Cornell University. He was a student of someone you may have heard of. This is Hans Bethe. Hans Bethe has the wonderful credit of being the first person to understand how the stars shine. And there's a marvelous story about him being out on a date with his future wife, looking up at the stars and saying, "They are beautiful, aren't they? and I'm the only person who knows why they shine. A remarkable humanitarian, a tremendous scientist, and did a work that really was the precursor to all aspects of this year's Nobel Prize. I like this quote from Hans: "Always work on problems for which you possess an unfair advantage," and I try to live by that. So let's talk about condensed matter physics. This is a prize that's given for work in the area of condensed matter physics, and I want to tell you what condensed matter physics actually is. So these are benzene molecules, and those of us over 50 are shocked by this kind of picture every time we see it, because we grew up at a time where no one doubted the existence of atoms and molecules. Well, some people did, but you'd have to be crazy. On the other hand, we also all agreed that you have to be crazy to believe that you'd ever actually see them. And that all changed in the 80s with the revolutions that went along with scanning tunneling microscopy, atomic force microscopy, and other probes. And now we can actually look at benzene molecules sitting on a surface. So the question is, how do we go from these ingredients of matter that we don't really have any doubts about? In fact, we don't even really have any doubts about the laws that govern their interactions. But how do we go from those basic objects, something like 10 to the minus 10 meters across, assembling them together into billions and billions of strongly interacting agents so that radically new things happen, things that are inconceivable at the level of individual atoms and molecules? So that's really what condensed matter physics tries to do. It tries to say, let me assume I understand the building blocks. Now, what remarkable things happen when I put those building blocks together and let them interact with one another and then change conditions such as temperature or maybe external fields and so forth. So here are some things that can happen. They happen to be all forks. I'm not quite sure why I always pick forks, but there we go. But what could this? Atoms can assemble and form forks made of ice or metal or plastic or wood. And in the early days of condensed matter physics, we tried to understand why it is that atoms gave rise to these material properties that are all very familiar to us. In fact, many of those details were worked out fairly quickly once quantum mechanics appeared in the mid-20s. And nowadays, what we do is we try to roam much more deeply and more thoughtfully and try and understand what new possibilities there are. And we'll see an enormous range of possibilities. And the organization that takes place at the atomic level that gives rise to these macroscopic properties is what makes condensed matter useful. And so what we're really doing in some sense is trying to understand the atomic and molecular scale engineering that gives rise to this world of wonderful materials that we know and love. But in truth, most of us study the subject just because it's beautiful. We think there's something fundamental in going to large assemblies of systems and seeing how they interact and seeing how their interactions unfold to produce phases of matter, really for the sheer intellectual delight of it. So how is it that we go from ingredients to emergent collective phenomena? That's what we're going to explore today. So I like to think of the subject this way. Let me ask you to become an anatomist or a physiologist, and let me ask you to imagine that you know everything about the human body in great detail. Let's say perfectly. You understand all the veins and the arteries and the muscles and everything. You understand how they all work. You understand the regulatory systems and so forth. Even if you did, I think you'd be hard-pressed to say that if you take lots of copies of these and put them together, then you would end up with, say, something like a democracy, something like political parties, the way things assemble and the way things interact and so forth. You really would be quite imaginative to conceive of these dynamic, changing, complex entities as a result of the building blocks. And so that's the challenge of condensed matter. How do you start with elements that you have more or less complete control over of and understanding of, and turn that understanding into an understanding of what we experience, not only in the world as we know it, but also in extreme conditions of ultra-low temperatures, ultra-high magnetic fields, and more. So here are just some examples of the kind of emergent collective phenomena that we're going to touch on, and I'll begin with some very familiar ones. So you know that you can take an assembly of carbon atoms, and if you cool them down from a very high temperature in just the right way, you end up with something quite new, something quite different from carbon atoms. You end up with something that is see-through and very rigid. Here it is, here's a diamond. So something happened along the way when we cooled down. We went from some gas, maybe to a liquid, let's say, down to something that is really qualitatively different. I try and change the shape and it fights back, and in fact it fights back for all time. Why is that? How did that event occur, and how can we understand it? Here's another example. Here is a little piece of a superconductor. A superconducting state of matter is qualitatively different from a familiar metal, like a metal that your fork may be made of. It really is a quite striking new thermodynamic phase where quantum mechanics is at work at large. It's not just something that conducts electricity very well, it's something qualitatively new and quite spectacular. And there it is, sitting above a little magnet, levitating as they do. Well, here are liquid crystals, first discovered in 1888, the day that Georgia Tech opened its doors. Liquid crystals, as you know, are now part of a multi-billion-dollar industry. How can you go from little baseball bat-like molecules packed together to something qualitatively new that can exert torques throughout the medium in one way but not others, depending on how you grip onto those molecules? And here's a magnet, of course, familiar since antiquity. But what's going on in the box? What is it about the way that the electrons and the atoms are behaving inside that little cube there that allows electricity to flow, but also magnetism to occur? And here are two more exotic ones. Here's one called superfluid helium-4. You take the heavy isotope of helium. It's a gas. It's out there. You know it very well. You cool it down, pretty cold, roughly 2 Kelvin above absolute zero. And what happens? It goes into a completely new state of matter with quantum mechanics working across the entire container. No viscosity. It will flow up the sides of the walls here. If I make a rubber ring and I fill it with superfluid and I push that superfluid round, unlike what would happen with bath water, which would slow down, that superfluid will flow essentially for the age of the universe. And so that's another quite exotic state of matter. And here's one that I won't go into any detail today. It's called superfluid helium-3. It emerges when we cool down the light isotope of helium. All that's different about the two versions of helium is that one has an extra neutron in the nucleus, and nevertheless qualitatively different. You have to go down to millikelvin temperatures, and then something quite remarkable happens. And the Nobel Prize was awarded to Osheroff, Richardson, and Lee for noticing these little glitches. So you have to be a very careful experimentalist and trust your data and not assume that a bus drove past the lab at that stage. But as Pasteur said, chance favors the prepared mind, and they realized that there was something quite radical going on here. So those are a few emergent states of matter known by the 70s. But there are many more, and I'm not going to talk about them in detail, but here's just a list: the fractional quantum Hall effect, antiferromagnets, some liquid crystals, and many more. I'll highlight one: topological insulators, hugely popular at the moment, really one of the main subjects in all of condensed matter and theoretical physics nowadays. So these are just a few of the kind of exotic states. So when somebody casually says to you, I know what the phases of matter are, gas, liquid, and solid, you can say, There's many, many, and they all have qualitative differences to them, and our job is to figure out why they happen, what is common about them, and what is different about them. So what does condensed matter physics bring? Why should we do it? Well, I think there are many reasons, but for me, first of all, there's beauty. The subject just has an intrinsic beauty to it, and we'll see why later on. There's a deep concept called universality that I want to touch on if I have time, and it gives a great kind of synthesizing, organizing principle behind the subject. Then there is applied impact. The fact is, condensed matter really has changed the world. We all use silicon devices all the time, every day, completely revolutionized the world. I was privileged to share a floor of a physics department with the great John Bardeen, who, as you know, invented the transistor along with Bratton and Shockley. And the impact that this has had is almost inconceivable. In fact, if we hadn't experienced it, we would never believe that such a revolution could take place emerging from condensed matter physics. But then there's also what I'll call fundamental impact. Ideas that emerge from condensed matter physics often take root in other fields, in the field of cold atoms, in the field of high energy physics. There's a great synthesis, flourishing of transfer of ideas between different fields of physics, and many of those ideas come into condensed matter from elsewhere, but many also go out from condensed matter into other fields. Let's turn away from condensed matter to topology, because one of the key words in the acknowledgement of this year's Nobel Prize was topology. Topological phase transitions, we'll see what they are, and topological phases, we'll see what they are too. So let me just remind you what topology is. The study of geometric properties and spatial relations unaffected, this is the key point, unaffected by the continuous change of shape or sizes of figures. And the subject has a wonderful history. It goes back to Leonhard Euler, the great Swiss mathematician. And Euler was struck by the following puzzle that the citizens of Königsberg, now Kaliningrad, formerly in Prussia, came up with. So here's a map of Königsberg, and here's a river, and you can see that the river has 7 bridges. They happen to be green here, and there happen to be 4 land masses, here, 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 and here. And so the question, and many of you will know this already, went like this. Can I start at a certain place, walk across all the bridges once and once only, and end somewhere else? Can that be done? And people didn't know. And so they would do the experiment. But what was better was Euler to come along and develop a brand new branch of mathematics, which he recognized right away. He called it the geometry of position, and he understood that there was something more to geometry than measuring distances. There was something more sort of loose and general, and that was the subject of topology, which he invented. And he managed to show that, in fact, by thinking about the bridges of Königsberg as this graph theory problem, which he invented, he was able to prove that, in fact, it was a waste of time to try, because, in fact, no matter how hard you try, there is no way to walk across the 7 bridges of Königsberg and crossing each once and once only. So that's the birth of topology. The version of topology that we're going to talk about today is a little bit different, and it really is exemplified by a beautiful result that all mathematicians know called the Gauss-Bonnet theorem. I'm not going to prove anything or do anything technical to you, but I want you to imagine that you have this kind of double-ringed donut. There it is. And I want you to think about a concept called curvature. How curved is that little region? And one way to answer the question how curved it is to take a path through the region and ask how curved it is, and then ask how curved that little line is as you rotate it. And you're going to collect together the minimum and maximum of the curvatures that you find and take their product. And that's called the Gaussian curvature, after perhaps the greatest mathematician ever, Gauss. So what Gauss and Bonnet discovered was the following. You compute that curvature at a little patch here, and then you repeat all over this object, and you add up the answer. So that's a reasonable thing to do. And a reasonable person would say you'll get an answer, which is some kind of number. But if you deform this object, surely that number will change, because when you deform the object, everything's changing. And it's certainly true that the local contribution from this patch is likely to change, but when you add up over the whole entity, a miracle happens, and you get an answer that does not change, provided you make deformations that leave the number of holes equal to 2. So this is the celebrated Gauss-Bonnet theorem, that the integral of the Gaussian curvature over the surface gives us something, or the integral of the Gaussian curvature is something very geometrical. It's to do with measuring curvature, but the answer is to do with something topological. It only cares about the number of holes, which is called the genus, which in this case is 2. And so whatever shape you choose, you will end up with 2 minus 4, which is minus 2. So the idea is this. There are branches of mathematics in which you can tweak and pull and push various objects, and nothing happens until something dramatic happens, and then a click happens, and something changes by a concrete amount. And I don't know what sort of email comes in, but as dean, I'm going to turn it off. Gone, gone, and gone. Good. All right. I can relax now. So the idea is that we're going to deform entities, and we'll see that those entities are the way that matter is organized, and we'll see that sometimes things change and sometimes they don't, and we're going to be especially interested in the situation where things don't change until they click and something qualitatively new happens. So let's get back to condensed matter physics. What's in the box? Well, all sorts of things can be in the box, and we'll see various examples. In the box could be atoms or ions. They could be molecules. They could be electrons carrying their spins. There could be rod-like molecules or disk-like molecules, all sorts of things. The individual ones, as I said before, we're going to imagine we know everything about. Now what happens when we put them together? Cool them down, push them, squeeze them, apply electric fields, apply magnetic fields, so on and so forth. And those entities come with degrees of freedom, and those degrees of freedom tell us how the entity can move. The atoms can simply move, the electrons can move, but their spins can reorient, and so on. And we're going to be particularly interested at the end of today's talk in situations where these motions are governed by quantum mechanics. But for now, we're going to keep in the classical realm. So the question is, how do we get from the building blocks of matter to the fact that this table is relatively rigid? How do we do that? Well, as we'll talk about in a minute, it's hopeless to just write down the equations that describe the motions and try and solve them. It's just inconceivable. We don't have enough paper in the universe, and even if we did, we wouldn't know what to do with the answers. So we have to be a little bit more thoughtful, and the first thing we can do is we can recognize that, in fact, many of the things that I measure today are the same if I measure them tomorrow and next week and the week after that. And even though what's in the box is all moving around and stirring and rearranging. And so a beautiful idea arose at the end of the 1800s that we can get the correct answers by averaging over all the ways to be and all the ways to move. And so the connection between the microscopic world and the macroscopic world comes about by taking the microscopic world and averaging over all the different ways that it can be and move, except that we have to keep track of certain constraints. We know that energy is conserved, so we better not let that vary, and that gives rise to the concept of temperature. We know that the volume of a container might be fixed, and that gives rise to the concept of pressure, and so on and so forth. And in fact, there are some subtleties here. Those of you who've studied the thermodynamics of liquids and gases may have wondered why those thermodynamics are different from the thermodynamics of crystals. And there's an answer. We won't go into it now, but we can talk about that later on. But the key idea is that we're going to do mechanics just as all good reductionist scientists would do. We know what's in the box and we know what laws describe them, but we're going to do that mechanics statistically by averaging and collecting together all the different ways to behave. And in doing so, we're going to learn something about the way the matter behaves en masse and on rather large timescales, by which I mean human timescales. So we're going to do what statistical mechanics people do, and we're going to look at a model. And I want you to think at the moment that the model looks very special and very unnatural. And your instincts would be right if that's your reaction. But I'm going to prove to you by the end of the lecture that, in fact, there is a wide latitude of physics situations that are adequately described by this kind of very, very simple model. So you may be tempted to say, well, gosh, I don't care about this particular model. I'm going to switch off. But let me urge you not to, because within models, there is, in fact, a validity that even transcends the validity of what we perceive to be more accurate descriptions of the matter at hand. So let me imagine you to think of a lattice, but I want you to think of it as 3D. So it's extending in and out of the board, and it's also extending up and down and left and right. And I want you to populate this lattice, which is frozen, the points aren't moving, populate it with what I'll call a planar spin. What's a planar spin? It's a little arrow. There's one of them tagged to each lattice site, and all it can do is rotate in the plane. Even though the lattice is 3D, I'm going to fix that spin to rotate in the plane. So that now is a large system that has lots of degrees of freedom. There's an enormous number of configurations because every one of those planar spins can independently rotate around. And we're going to try and think about the behavior of this kind of system. So there's our large 3D lattice, our planar spin, and we're going to imagine a law of interaction that could hardly be simpler. It just says take every pair of neighboring spins and make the energy low when they're parallel and make the energy big when they're anti-parallel. Parallel means low energy, anti-parallel means high energy, and that can be modeled by a simple cosine function. J just tells us how strongly these neighbors are talking to each other, how strongly they are coupled to one another. And we want to understand, or at least think a little bit, about the behavior of this model system. So let's imagine that we're at very high temperatures. Very high temperatures means the average energy of the system is really high. And if the average energy is really high, then these little forces between neighbors don't really matter very much. And you can see that in this picture. This is a typical snapshot of what's going on, and you can see that there's just chaos. these arrows are just pointing all over the place, very little coherence, very little organization at all. There's a little box there, and I want you to imagine watching that box for a long time and asking what happens, and what you'll learn is that the spin in that box over the course of time will reorient and reorient many, many times. So if you ask what is the average value or average direction of that arrow, the answer is there isn't one, it's 0. So the system remains in what we call a symmetrical state. Anything that you measure will have as much symmetry as the laws governing the interactions between the agents, and those laws are invariant. If I rotate pairs around, the cosine of the angle between them stays the same, and therefore this physical state of matter is, we say, symmetrical or symmetry unbroken. We can also ask, how strongly does this system respond if I apply a kind of push that tries to align the spins upwards? And what we can learn is that the response will be basically the response of an individual one of these little spins multiplied by the number of them. So they all act independently, and so even though there's a kind of energy gain by pushing them to align, there's so much entropy associated with the disorganization that it's very hard to herd these cats and get them to sort of organize. Well, what happens if we lower the energy a bit? Well, what we then see is that the effects of these interactions begin to take over. We begin to get the different spins talking to each other in a way that is not disrupted by temperature. And you can see there's a little patch here. I'll call this a local conspiracy. People all agree to point in the same direction. It comes and goes. It's fleeting, but it is there, and it has an impact, because this little region here, if I then try and orient the spins, will respond collectively. It'll respond together and be rather easily turned. The effects of heat are smaller. So we get these emerging conspiracies and what I'll call short-range organization, but far away, it's very hard to tell that something special was going on here by looking over here. Still, if I look in this box, no direction gets picked out, and I still have what's called an unbroken symmetry. Now let me cool the system down. What happens now is that this patch grows and grows and grows, and eventually it takes over the whole system. And so I'll call that a global revolution. There's a conspiracy now between everything in the box, more or less, subject to a few renegades that flip and flop here and there. But by and large, the system more or less agrees what to do. And in doing so, it picks out a preferred direction. And I think your eyes will tell you that up is somehow special, whereas it wasn't here and here. And if I now watch in this little box for a long time, there's a preferred direction. And so, quite remarkably, a physical system that has laws that didn't know anything different about the different directions that my hand is pointing in has picked out a way to behave that chooses a fixed direction. And that's a pretty remarkable thing. And it's this mechanism of what's called spontaneous symmetry breaking that is behind a great deal of the useful properties that we see in nature. It's behind magnetism, it's behind superconductivity, it's behind the rigidity that you know simply of a plastic ruler and so forth. And so this phenomenon that the physically useful properties result from some kind of loss of symmetry of the original system is really at the heart of condensed matter and the varieties of behavior that it shows. So this is a very sort of canonical, a very sort of standard progression from a high temperature to a low temperature phase with something dramatic, we call it a phase transition, happening in between. And let me remind you that this is a three-dimensional system. It's just that I only drew a sheet. I should have drawn a stack of sheets extending throughout the page. So again, it looks like a pretty special model, but we're going to see shortly that it isn't. Let me get a little bit closer so I can turn the page. So here's what we've seen so far. We've seen that organization emerges as we cool systems down. There are these conspiracies of spins and conspiracies of atoms and conspiracies of electrons, or conspiracies of rod-like molecules as we range through the possibilities of condensed matter. And that organization has a strong impact on how responsive the medium is to pulling and pushing on it. And ultimately, it gives rise to uses. And I've just listed a few here. We get rigid solids instead of liquids. We get permanent magnets instead of induced magnets. We get liquid crystals where we can grip hold of the rod-like molecules and they can twist through our display and be useful. We get helium-4 that can be used, for example, in subtle gyroscopes and we get superconductivity, where we can make a mile of dirty lead wire in a loop and have supercurrent flowing around it for the age of the universe, because that supercurrent is gripping onto itself, locking tight through something a bit more subtle called the rigidity of the quantum wave function. And if we talk a little bit about pulling and pushing, we can ask what happens for the hot system. If we pull and push, if we push more and more, we get a little bit more response. On the other hand, if we cool things down, we get a big response for a little push. And if we make things so cold, then in fact we don't even have to push at all, and we still get a magnet or a superconductor, and so forth. So this is a kind of standard picture of what happens in many, many settings of condensed matter physics. And all of this was synthesized quite beautifully by the great Russian theoretical physicist Lev Landau. And I will call this a kind of geometrical paradigm. And I like this picture because nothing could be more geometrical than Landau playing tennis here. But the basic idea goes like this. Let's go back to our box. And what were we doing? We were looking in the box and inspecting the fact that this direction seems to be picked out and preferred when the system, let me say, freezes. Well, what Landau was the first to realize in general terms was that idea is true even more generally. And I'm messing up here, so let me start again. I think I'm too far away. So let me go here, and here's Landau. So what Landau said was, look in the box, find something geometrical, watch it for a long time, and average its behavior. So that could be, for example, whether or not there is a sodium ion in a little box. If I have a molten ionic solid, I will get motion in and out of the different species with none preferred. But if I get a crystal, then sitting in the box will be a particular ion, although it may jiggle just a little bit back and forth, but I will get something special in the box. So this is geometrical order, and all the examples we've talked about so far, one way or another, it may be a little bit subtle, but one way or another, have this Landau version of geometrical order. Now, what earned Kosterlitz and Thouless the Nobel Prize was the recognition that it didn't have to be this way, and if it were not this way, it need not be boring. So that's what Kosterlitz and Thouless discovered. So let me take you through the kind of philosophical underpinnings of their discovery. They realized that there is a setting, a model, but it pertains to many physical things, in which this idea of broken symmetry, the idea that things freeze in a detectable way where I can look and I can see a preferred direction to my arrow, that is ruled out. It's ruled out because the system, for example, is very thin and there aren't enough neighbors to help things sort of self-consistently decide which way to point. On the other hand, they may still at low temperatures be more organized than not organized at all. So instead of saying broken symmetry organized or molten and disorganized, they identified a new possibility in which matter is organized, but it's organized more subtly. As we'll see, it's organized topologically rather than geometrically, and that's what we're going to come to now. So here is their, and again, I'm turning too many pages, so let me go back. Here is their paradigm. At high temperatures, just as we saw in our snapshots, only if we look very locally do we see alignment, but if we go a few lattice sites away, everything is sort of incoherent and independent. That's what would happen if we had something that could be superfluid but was too hot, or could be magnetic but was too hot, or could be superconducting was too hot, could be rigid but too hot. They're saying, now if we cool things down, we might not get long-range order, this crystallinity that runs through the crystal, but we're going to get something that's pretty darn close. It's about as close as you can get without being ordered. And I'll explain what that means shortly and describe it. And this was the first example of a topological phase of matter ever realized. So let's go back to our model. All we're going to do is take the model we had and thin it down to one layer or a few layers. Actually, it doesn't have to be one, but let's pretend that it's just one. So here's our set of sites, but it's now 2, not 3D. We're going to populate it with spins, just as we did before, and we're going to choose an interaction law between the spins that favors alignment with a strength given by a constant that we're going to call J, that sets a kind of energy scale. Now, where is it that topology comes in? Let's see where topology comes in. Well, what we can do is we can go to very low temperatures where all the spins we think ought to be aligned. We'll see later that they're not, but we imagine that they all aligned and that interaction wins. And then we make very gentle excitations. They're called spin waves. They're just kind of ripples. The simplest thing you can do to everything be aligned is just push everything away a little bit. It has low energy, so even when things are cold, these excitations happen. And it turns out that in 2 dimensions, there are lots of these excitations, and there are enough of them to say, even if you thought and started with an aligned system, if the temperature is above 0, these ripples will destroy the ordering. So there won't be any alignment. And if I look in the box and wait over time, in fact, all orientations will appear with equal probability. So I destroy broken symmetry, but there's a strong vestige of it left called quasi-long-range order. On the other hand, there's a whole class of excitations that are topologically distinct from these spin waves. I can't create those excitations by any sort of just local rearrangements. I have to do something more radical. I have to change the class of the configuration. And the typical configurations that, in fact, have this impact as qualitatively different from the impact of these are called vortex excitations. And you can see they kind of look like water swirling around. This one doesn't look like that so much, but it turns out to have the same effect. So these are the kind of excitations that, if present, would destroy this quasi-long-range order and replace the system by just the usual high-temperature, not very aligned phase. Well, then the question is, do these happen? And Kosterlitz and Thouless made a very simple argument to say they do. But before we get to it, let's have a look at topology. So here's our spin system, and we're going to track the orientations of the spins around this loop. So we're going to follow that loop and ask, where do the spins stay? Well, at this red site, we're pointing north and just a little bit to the east. As we come around here to the blue site, we got a little bit more north, and by the time we get round through green and back to red, we've sort of undone this loop. And the fact that this loop only rattles back and forth but doesn't encircle is enough to tell us that we can undo this, ripple, this spin wave away from perfect alignment without having to do radical surgery. On the other hand, if we take a vortex and we play the same game and we follow where the spins point as we move around this loop, we'll see, and you can see it here, that at red and then at blue and then at green, the spins wrap around, and that loop is hard to get away from. We're kind of stuck with it. It's what's called a topological excitation. And Kosterlitz and Thouless realized that these vortex excitations would play a critical role. And let's see how they do. So what they asked is, when do they matter? And they looked at the energy and the entropy for vortex excitations, and this is what they found. If they add a vortex, the energy goes up, and it goes up a lot. It goes up because that vortex reaches as far away as you can go. It reaches fairly weakly when it's far away, but there's a lot of far away there to add up and contribute to the energy and give this so-called logarithmic divergence of the energy of a vortex that grows with the size of the system. And then they asked themselves, what about the entropy? Well, the entropy counts how many places the vortex can be, and its center can more or less sit at every lattice site. So again, they get an entropy, which is the logarithm of the square of the lattice size, which is the number of lattice sites. And they made a simple argument, backed up by detailed calculations, that at low temperatures, the energy would win, and at high temperatures, the entropy would win, and that change would take place when the strength of the interactions was the same as the temperature in suitable units. And so they suggested that there would be a transition from one in which the vortices were bound together, and that would be the phase that effectively has no vortices, because if you look at long enough length scales, you don't see them because they're nestled next to one another and they're effectively invisible, to a regime where the vortices can unbind and one can go one way and one can go the other way, and you then have a plasma of vortices. And so there was a kind of phase transition without any breaking of symmetry, but these vortices, once they proliferate, would scramble the spins and take us to the high temperature phase. And so that's exactly what happens. If we ask what happens as a function of temperature, cooling down we reach a special temperature. At high temperatures, entropy wins. At low temperatures, energy wins. At high temperatures, there are lots of vortices and anti-vortices. At low temperatures, they're bound together. If we ask the following question, if I hold a spin up over here, over what region of space will I typically then find the spins also to be biased up? That's called a correlation function, and it's a useful diagnostic. What you find at high temperatures, because of the vortices, is that the likelihood to point in the same direction decays very quickly, in fact, exponentially quickly. But if you are in this quasi-long-range ordered phase, that is at low temperatures, then that is not a slash, it should go there, sorry. You have at low temperatures the vortices bound, and now if I push a spin up over here, there will be a very, very, very large region, qualitatively bigger because the region falls off like a power law with, the strength falls off like a power law with distance rather than exponential, describing this low temperature phase. There are other topological diagnostics that I won't go into to do with how many vortices you find in an area, and that's qualitatively different in the two phases. Physically, something quite dramatic happens. If I make a thin film of superfluid, these are helium-4 atoms cooled to a low temperature, and I put them in this annulus like this. It can have a little depth to it, but put them in an annulus and create superflow. At low temperatures, below the Kosterlitz-Thouless phase transition, that superflow, even though there's no broken symmetry, will go on forever, because to destroy it, we have to move a vortex one way and an anti-vortex the other way, but they're bound together, so that doesn't happen. So we really have qualitatively new response, qualitatively new organization, and a qualitatively new phase of matter. So I want to just wrap up this story about the Kosterlitz-Thouless transition by talking about two superheroes of mine, both sadly passed away quite recently, Leo Kadanoff and Ken Wilson, who were pioneers of a philosophical edifice that has really transformed the way we think about theoretical physics. And this took place in the 60s and 70s and really dominates and guides our thinking to the present day. It goes by the name of Universality and the renormalization group, and I won't go into details, but I want to answer the following question. So I said that model was kind of special and unnatural, and I'm now going to tell you that it isn't. It's actually very generic, and large classes of systems are controlled by this model. Here are some. We can make magnets where the atomic spins point in the plane. That can be done. We can make them thin. We can make superfluid films. It's done routinely in the lab. We can make thin films of superconducting material also. And actually, you may not see this. It's not immediately obvious. But in fact, this Kosterlitz-Thouless theory is very closely related to the question, what would happen if I took a crystal and I made it two-dimensional? And I asked what happened as I heat it up. And the unbinding of dislocations in the crystal is very similar to the unbinding of vortex-anti-vortex pairs in the Kosterlitz-Thouless model. So there are many problems in classical physics and also in quantum physics, as we'll see in a minute, that are governed by this circle of ideas. But what I want to tell you is this. After Kadanoff and Wilson, physicists and others understood that, in fact, almost nothing about the model matters. So I said we had these little spins and we had a square lattice. I said we had 3 dimensions or 2, and then I said the spins stay in the plane. Out of all that information, the only thing that matters is that the spins live in the plane and the lattice is 3-dimensional, and that the force law just reaches out to neighbors and doesn't go very far afield. Almost nothing. And what we have learned over time is that as one looks at longer and longer length scales, starting with atoms and ending up with the kind of buckets of material that we might imagine in the laboratory, almost all of the technical details, what type of atoms were they, what type of molecules, almost all those details get washed away little by little as we progress out to longer and longer length scales. And at the end, almost nothing matters, really just symmetry and dimensionality. And actually, this is in some way why we can do physics at all. So I just want to tease you with a kind of puzzle. You all know that mercury is a liquid at room temperature, and it's quite a different kind of liquid than, say, water. And yet the flow of both is governed by the Navier-Stokes equations. Sure, you have to tweak a couple of parameters, maybe the viscosity and the density, but the structure of the theory is the same. Same goes with elasticity. You might be looking at the elasticity of rubber or the elasticity of wood, and yet it's still Cauchy elasticity. How can that be? Everything about the atomic structure just ends up buried in a small number of parameters, but the structure of the theory remains the same. So this idea of emerging universality is a deep and powerful one. Let me not talk about how we use topology to understand defects in other sorts of media, but let me go to quantum mechanics and wrap things up. So I'm going to talk about a beautiful piece of work that was done by David Thouless and his collaborators to understand a remarkable phenomenon called the quantum Hall effect. And you'll see some connections in a minute. So here goes. So a long time ago, Edwin Hall was reading Maxwell's book on electrodynamics, and he noticed something curious. Actually, he noticed something that Maxwell was wrong about. And he set to do an experiment. And the experiment went like this. He took a gold leaf. It's macroscopic, not atomically thin. But he took a gold leaf, and he passed a current in this direction. That's called I. He applied a magnetic field, strong for the day, in this direction. And remember that the magnetic field causes the charged particle motion to be deflected, and so that builds up, deflected this way, that builds up a potential difference or voltage between these two sides. And Hall noticed that there was a linear relationship between how much current he pushed and how much voltage he measured, and that relationship was characterized by something called the Hall conductance, and it depends on how strong the magnetic field is. So there's been interested in the Hall conductance for a long time. It tells us all sorts of properties of what's carrying the charge about. Let's fast forward 100 years to German scientist Klaus von Klitzing, working in France at the time, with a very clean system, very much like this, except it really was atomically thin. In fact, it was an interface between two different media and a gas of electrons able to just glide in 2 dimensions and bounce off almost nothing impure. He cooled the system down, and he applied a strong magnetic field, and he measured the Hall resistance, and he found something truly astonishing. So as he turned up the magnetic field, the Hall resistance grew, just as expected, but then it developed wiggles, and the wiggles got flatter and flatter, and here they are. In fact, even more exotic things happen up here, but I won't talk about that today. Remember, this is a macroscopic sample. You can look at it. It's big. It's got 10 to the 20-something particles in it, and it's not made perfectly, and the lab isn't made perfectly, and the magnetic field isn't uniform, and the voltmeter isn't perfect, and so forth. How accurate is this flatness? It's accurate to about 1 part in 1,000 million. So this is like counting the number of people on Earth to within about 7. Pretty accurate. For this schmutz, this stuff that was just baked in the lab. I mean, it's more delicate than that. It was a beautifully created sample, but it's by no means perfect. Nevertheless, this, what we call quantization, emerged, and more than that, when you ask what value the resistance or the conductance has, if you measure the conductance, it turns out to be a natural number times something that we know of from the world of atoms, but we don't really think of at the macroscopic world. It depends on the charge on the electron, and it depends on Planck's constant from quantum mechanics, and nothing else. And when you have a result like this, in which the answer doesn't depend on the stuff in the box, it cries out for a generic explanation. And a beautiful explanation was put forward by Bob Laughlin, and for that work and other, he won the Nobel Prize later. But I want to tell you about David Thouless' contribution, because it really brings out the topology of the subject. So this is what David Thouless did. He looked at this formula with collaborators, and he said, how can I get this integer? We've seen that topology gives us integers. We saw the Gauss-Bonnet formula, and everything only hinged on the number of holes in the object. We saw these vortices. There was either a vortex or there wasn't. What could be going on here that gives rise to this quantization? And what David and company did was they managed to rewrite the formula for the conductance in terms of these physical entities. And this is actually a very straightforward derivation and an integral. It doesn't really matter what the integral is about. It just collects up contributions from different electronic wave functions. But the amazing thing is this construct here turns out to be a generalization of the Gauss-Bonnet theorem. due to the great mathematician Chern. And so this quantity, built from the wave functions of the crystal, has the character of Gauss-Bonnet in the sense that if I change the crystal, move atoms around, put a little bit of dirt or disorder in, these numbers all change, but by the time I integrate, all the changes cancel out, and I get a simple answer called the Chern number. And I won't go into the details, but the key point is that from a Schmutz-dependent entity here, whatever's in the box, you end up with something in the bigger box that is just, can be nothing but an integer. And so David and company really understood why the quantum Hall effect had this remarkable stability to it, why you should get this precision to 1 part in 100 million. So let me wrap up by talking about Duncan Haldane, who I haven't talked about very much today. But let me turn to Duncan. He's a Princeton physicist. In fact, like all three, Cambridge educated and spent most of their careers in the United States. And unfortunately, there's no adiabatic continuity between that fact and winning the Nobel Prize. So what did Duncan do? So again, we're going to look at a model, but we're going to see that the model actually has a much richer generality to it. So once again, we're going to take spins. Here they are. There's a little spin, but now they point in any direction. So they're three-dimensional spins. On the other hand, the spins just live on a line. There's just one on each line. And in fact, you can make physical samples that, in effect, behave like this. So there is this chain of spins. And the spins interact with one another, in fact, in such a way that the nearest neighbors would kind of like to point in opposite directions. So this is called a quantum antiferromagnet. And in fact, Hans Bethe, who we talked about right at the beginning, David Thouless' PhD advisor, was one of the pioneers of the physics of one-dimensional quantum antiferromagnets. So here's our lattice, and here are our spins. But the big difference is that these spins are now quantum spins. Like all quantum mechanical objects, they're subject to uncertainty relations, and they jiggle and they wiggle even when they are in their lowest energy state. So this is the quantum spin chain that Duncan Haldane worked on. And you may remember from quantum mechanics that spins can be spin half, like the electron, or spin 1, or spin 3 halves, like some nuclei, or spin 2. There are two types of spins, what we call integer spins and half-integer spins. And Duncan was very interested in the difference in behavior of these spin chains when you change the spin from a spin half to a spin 1, from a spin 1 to a spin 3 halves, and so on and so forth. And he discovered something quite dramatic, as I'll explain in a minute. So he wanted to know what is the quantum mechanical ground state, the lowest possible energy level, what is the wave function for this extended quantum system? And he wanted to know what is its character. If I hold a spin up here, over what region of space will that holding up propagate? Will it be short-ranged with some kind of exponential decay, or will it be long-range with some kind of algebraic tail falling off very slowly like a power law? So that was the question. And this question of whether or not there's short-range order or quasi-long-range order is totally connected to the question of whether or not above the ground state you have to go a finite energy to find a new state, or whether there are states infinitesimally close in energy to the ground state. That's the question of whether or not there is a gap or not. So how did Duncan tackle this problem? There's just a couple more slides. So let me remind you of a story that Feynman taught us just after the Second World War. Let's stick with particles, not spins, just for a minute. And let's suppose the particle moves on a line. And we can ask the following question. Suppose I prepare the particle here, and I want to know the answer to the question, what is the amplitude to find it here at some later time? So we can answer that question by solving the Schrödinger equation, but Feynman said do something else. He said collect together all paths that start here and jiggle back and forth and end here at some later time. And if you lay time out this way, the paths look like this. And he said, this is Feynman speaking, take the path, compute a certain physical quantity for that called the action of the path, and divide by a fundamental constant called Planck's constant, and stick that in an exponential, and add that up for all vastly infinitely many paths. And it turns out you can actually do that for simple problems, and you in fact get the same answer as the Schrödinger equation gives you. You can repeat this process for spins. You can ask the question, if I prepare a spin pointing down here, and I want to know the chance of finding it up here at some later time, well, I have to look at all possible ways the spin can contort and wiggle and point in different directions as long as it ends up here. And I follow the same kind of Feynman procedure. I sum over all trajectories for the spins of a kind of entity here, and this so-called path integral tells me about the dynamics of the spin. So what did Duncan do? Duncan said, let's apply this procedure to all the spins, and they're laid out here in space. There's a spin everywhere out here in space. And let me ask how they unfold in time during different orientations. And Duncan realized that there is a beautiful class of ways to get from the present to the future that involve topological excitations of the spins en route. And so you can see that the spin in the middle here leans back outwards and points down and then rotates and then stands up again. Whereas the spins out here do something different. They just kind of tilt outwards and back again. And this class of excitations is called a topological excitation, and it turns out to behave fantastically subtly differently for integer and half-integer spins. For integer spins, in fact, they essentially have very little effect. And what happens is you end up with integer spins for having just what you'd expect, namely short-range order. Hold a spin up, and only the nearby spins point up, modulo something called a stagger that I won't mention anymore. On the other hand, for half-integral spins, like electrons, which are spin half, something qualitatively different happens, and that gap that you have for integer spins gets destroyed, and you end up with gaplessness. You have long-range correlations, and you have a qualitatively new phase of matter, a topological phase of matter, not the Kosterlitz-Thouless one, but similar in spirit to the Kosterlitz-Thouless one because it has what's called quasi-long-range order. And this beautiful idea has spawned an enormous amount of work in the intervening years since the early 80s when Haldane made this and other seminal discoveries. So I'm going to stop, and I'm going to stop by saying that low-dimensional systems continue to surprise 30 years later and more. The early ideas have continued not just to be interesting, but to have catalyzed tremendous new areas reaching into elementary particle physics and many other domains. What started out as theorists' dreams, idealized models, has been overtaken, caught up, and even overtaken by our experimentalist colleagues who make remarkable exotic materials that realize the behaviors I've talked about and much more. And we're now in the midst of what I'll call the third topological revolution. The first was Kosterlitz-Thouless, the second was the integer and fractional quantum Hall effect, and the latest one gives us tremendously exciting materials such as topological insulators and topological superconductors, which may turn out to be wonderful materials for the subject of quantum computing. And let me say thank you very much and stay tuned.
I think we have a few minutes for questions. We have a microphone, so if you have a question, just to raise your hand, I'll bring the microphone around so that everyone can hear the question.
But by the way, those of you who need to go, of course, feel free.
Let's see. Let's give it just 10 seconds for the people that are leaving.
Should I wait, or should I wait 10 seconds? Oh, what's the difference between a vortex and an anti-vortex?
So what's the difference between a vortex and an anti-vortex? If you bring a vortex together with a vortex and you merge them, you get a vortex that is twice as strong, and the spin wraps around twice on the way round. On the other hand, if you bring a vortex together with an anti-vortex and merge them, they annihilate, and it's as if there were no vortices there at all. In fact, if you have no vortices, you can create vortices and anti-vortices out of nothing.
Thank you for a wonderful talk, and I'm going to be that person and ask what's being done here at Georgia Tech with regards to this area of research?
Yeah, so a great deal. So the question is, what's going on here in this area? There's a great deal of work, I would say, mostly in the physics department. Zhigang Jiang is doing beautiful work on topological superconductors and related topics. Martin Murigal is doing wonderful work on exotic magnetism, which is closely related to some of the ideas I talked about today. Claire Berger, Walt de Heer, and Phil First and Ed Conrad and Marcus Kinderman are living in the flatland of graphene and doing quite extraordinary, exciting work as well. And I'm very sorry to the folks who I didn't mention, but that's certainly a wonderful crew. So yes, this subject is alive and well at Georgia Tech.
Thanks, Paul. Great talk. I have a question. Why now? Why is it given now, the timing of it?
Yeah. So this is let me speculate and let me edit the film. I think this is a prize that, in fact, those of us who every now and again have a little betting pool on Nobel Prizes were betting on in the 90s and early 2000s, and then it sort of went away. And I think I'm speaking for myself, and actually Jenny, my wife, will verify that I have predicted this one in the past, and I predicted Bob Dylan as well. I think one of the reasons is there has been an absolutely extraordinary surge in interest in topological materials over about the past 6 years, and like often happens very healthily in science, the surge is not only theoretical or only experimental, but a really inspired partnership between the two communities that has led to predictions of topological materials, all sorts of new ones, even in 3 dimensions. The manufacture and experimental measurement of such materials, and the sense in the community that the robustness of the properties of these materials make them excellent candidates for quantum computing. So I think it's a confluence of those 3 themes that has created a surge in excitement of Revolution 3 in topological materials, which I think inspired our friends in Stockholm to check in on Revolutions 1 and 2.
Are there any other questions? One here. Last one.
What makes these types of materials amicable to quantum computing?
Yeah. So in quantum computing, the biggest challenge is not the ideas, but the sheer experimental challenge of maintaining what we call phase coherence. So the quantum interference, which is one of the key ingredients in quantum computing, is rather delicate and rather prone to destruction from outside agencies. And so what you look for are situations in which the quantum coherence has a kind of robustness to it. And for various reasons, topological materials are endowed with a kind of robustness that makes them very suitable kinds of objects.
Okay, let's thank Dean Goldbart one more time. If you have a question still, you can come down to the front.